It's a real pleasure today to have Xenia de la Ossa and Philip Candelas speaking to us, who are visiting from the University of Oxford. I was wondering if you could give us a brief biographical sketch. Where were you born? Where did you grow up? How did you become interested in maths and physics?
Well, I was born in Costa Rica from a Costa Rican father and a Salvadorian mother. And then I traveled quite a lot because of my father's work. So I lived in Mexico, in Colombia, in Guatemala. So all my studies were in different places. Mm-hmm. So I studied in many places. I ended up doing my undergraduate degree in Guatemala, mm-hmm. Universidad del Valle de Guatemala, which was at the time was a small university, and I had fantastic teachers there, rather inspired in fact. And then I started my first year in biology, but I was very taken by the maths and the physics courses. It was really my first time I encountered mathematics and mm-hmm. physics properly. And I enrolled in physics the following year. So I changed. So it was that first year with extremely inspiring teachers that
converted you.
They made the switch.
Uh-huh.
I still love biology though. Anyway, so then I went to do a master's in Costa Rica in theoretical physics, and then a PhD in Austin, Texas, mm-hmm. Again in theoretical physics, where I moved more and more into the mathematical side. So at the time, string theory was booming, so I went more and more into the mathematical side.
So what year was that roughly when you were doing your PhD?
I started in 1983.
Uh-huh.
Yeah. Then, I did a PhD there. I met Philip, married, we had children in the middle of my PhD. One child.
So you had your first child before graduating?
Yeah, in '86.
Uh-huh.
Yeah, that was different.
Mm-hmm.
Yeah. So
you wrote your thesis with a little baby around.
Yeah, exactly. And the last month of the thesis, I mean the older one, but I only had one at the time. We only had one at the time. So then from then on, it was a postdocing time, which was hard because then I had another baby.
Uh-huh.
The first, I went to Costa Rica for a year. In fact, after my PhD. Because I had a deal with them that I was supposed to come back.
Mm-hmm.
Because of the family circumstances that didn't work out later, so I made another deal with them. So I paid them back, basically.
Mm-hmm.
And then, because they had given me 2 years scholarship to Boston. So that was sad, but that was reality. So it was good to be there for a year and see what the issues were at the time. It was very difficult to do any research. There was a lot of teaching. Though I had some relief in the first year, to say. So then it was more postdocing until we went to Oxford, right? So it was quite a long postdocing period.
And what year did you move to Oxford?
99.
99?
Yes.
So it's a lot of postdocing.
A long postdocing.
Uh-huh.
And the problem is we had the two-body problem.
Yeah.
Because he had a permanent position. And so finding...
In Austin, yeah?
Yes, in Austin. Mm-hmm. So finding 2 jobs in similar areas was not so easy, right? So
mm-hmm.
It was difficult. So, but in the end, it worked out after difficult postdocing, I would say. I mean, for example, at the beginning, it wasn't so hard because we went to Switzerland and Philip was given leave of absence. But then I went to Princeton, and then Philip didn't have any more leave of absence. So Philip was commuting back and forth, basically every week. So that was not fun.
Not fun.
I wouldn't do it again. No.
Uh-huh.
No. Right. So, but anyway, so it worked out.
Yeah. And Philip?
So I was brought up in London. And then I suppose by the time I was about 15 or so, I mean, at the beginning I wasn't much taken with maths, but by the time I was 15 or so, I think it was clear that I was going to pursue some sort of career in mathematics, somehow broadly defined. And I was lucky enough to be admitted by Cambridge, so I did a first degree in Cambridge. And really based, I mean, it's scary looking back on how one makes decisions on no knowledge. But I decided that relativity was what I wanted to do. And I followed Dennis Sharma. Dennis Sharma was a cosmologist, and he had moved recently from Cambridge to Oxford, and I spoke to him. In those days, the application process was a lot less formal than it is now. You spoke to somebody and somebody made a recommendation and it was decided, and so I went to Oxford to do a PhD, which turned out to be officially in astrophysics, but actually it was the time of Hawking. Well, the Hawking-Penrose theorems were very recent and the subject of much discussion, and then Hawking came out with his discovery of Hawking radiation on black holes, and so I started looking at that, and I wrote a thesis on that. And towards the end of that, there was no postdocs at that time as such, but it was very important to sort of go to America. And there were various scholarships or systems that would take you to the States for a year. Or something. It was important to go for a year and come back. And I went, again, I just expressed this desire to Dennis one day, and he came in sometime later and said, I spoke to John Wheeler yesterday on the phone, and there's money to go to Texas. Wheeler was moving from Princeton to Texas. There's money to go to Texas if you want. So I said yes, and I went initially to Texas for a year. It's strange. You think that, well, I won't enjoy it. It's a remote place, and but the young man must be robust in pursuit of his career and so on. And I went, and it was a wonderful place. And the science was extremely exciting. There was a wonderful group in relativity. When it was a small subject, people interested in quantizing gravity, again, where that was not really part of physics according to the physics establishment.
So what year was that when you went to Austin?
So I went in 76. So I went initially for a year, and then I was asked if I'd like to stay, which meant that actually I had to come back for 3 months to finish up submitting my thesis.
So that was still pre.
That was still pre. It was all this. I'd like to go to the States, and it had been set up without even considering the fact that I hadn't finished. And but I was able. I went back. I wrote up what I'd written, what I'd worked on in the year in Austin. I got the certificate. I was able to go back as an assistant professor in September, and I was still there in 1999. So it was one of those things that you go for a year, but it turns into 21 years or something.
And so it wasn't difficult to move from the Oxford environment to the Texas
Oh, it was very different. But in many ways, it was very exciting. So all sorts of things. I mean, Austin is a great place to live. And people really are friendly. The weather is good most of the year, and when it's not good, it's too hot. But it's that's a liberating thing coming from the UK. And then it coincided with what was a heroic period in Austin, which was kicked off by the increase in the oil price. So the embargo on Iranian oil and so on, the embargo on, well, before the Iranian oil, Middle East oil, which was so harmful everywhere else. But the sudden increase in the price of oil meant that it was very favourable to drill. And Texas is the centre, Houston is the centre of the oil drilling industry, oil exploration industry worldwide. I mean, people drill for oil in the North Sea or in the Far East or wherever, but they still call home. When they call back to the office, they call Houston. And so there was suddenly a lot of money in the state and in the university and so on. And the university was keen to use this money to better itself. So it attracted people like Stephen Weinberg, who came. And that again was a heroic period because Steve came and he brought people, and he was very interested in gravity at that time. How you go from the standard model of elementary particles to incorporate gravity and perhaps produce a theory of everything. It was an exciting. He was very excited.
So just winding back a little bit to before you went to Cambridge, did you already envisage having an academic career?
I think I was one of the last of a generation where you didn't have to think so much. In the sense, I mean, postdocs now, if you're a postdoc, you send out 100 applications, and that's what everybody does.
Yeah.
And then you see what you get back. I never did that. I simply said I would like to go to the States for a year, and then somehow it was set up. And similarly, I didn't apply for my job in Austin. I mean, at some stage I must have applied, but I was asked, would you like this job? And it was some job that was associated with John Wheeler that they had, and they were having difficulty finding somebody for the job, and there was some danger that the job might revert to the dean if someone didn't take it, and I was perhaps the next warm body to walk down the corridor. And
maybe they also saw something in you.
Yes, but it didn't really. Yes, but all that was done without really thinking hard about, do I want to do 2 postdocs, which is what people do now, and pursue an academic career, or, as many of our people do, go into banking.
So you would say that as a 15-year-old, you were not, you just liked doing maths and physics?
Yes, so I was going to do maths or physics, and I thought, quantum gravity, that's the big problem. That was the problem that Einstein couldn't solve, and so on, and people have been trying to solve since. And of course, general relativity is beautiful, particle physics is fascinating. Putting those together is a great challenge, and so on. But I didn't have to make some of the policy decisions that people have to make now.
Interesting. And Xenia, did you see a career in academia, or did you love biology and just thought, I want to explore biology?
This grew up slowly, this idea of being an academic. When I started in biology, I wasn't thinking about that. Because I was thinking that I would do a career in biology and stay in Central America. Right? So, so it was, when I did my master's in Costa Rica, I had a very good supervisor, Guido Taramont, who encouraged me, and he was, at that stage, he was really key in encouraging me to go up to do a PhD. Right?
So he pushed you to go to America?
There was not pushing, it was a kind of conversation, I don't know what to say. But I did want to apply, I mean, but he was quite encouraging, both in relation to the work that we were doing at the time with the masters and going away. Right?
I find it so unsettling how, I had a few conversations with people as an undergraduate that had such an enormous influence on the rest of my life.
Yeah.
And those little discussions are so crucial.
Yeah, and it's only later that you realize this impact, right? That when you yourself ask the questions you're asking now, I mean, why do I do things? I mean, what motivated me? And then I became rather motivated to go to a PhD, rather intense. But I was working at the time. I started doing the master's even part-time, because I wasn't thinking of what happened. I was working in a lab, in chemistry, right? So I was trying to find which way to go at the time. So in the end, I did go on PhD, and then I liked the idea of being in academia while I was doing the PhD. I think it was at the time, because the research was rather motivating in a way, and you want to keep on doing that.
Of course. And did you feel the pressure to publish that postdocs feel today?
Yes, absolutely. Yeah, you do feel that pressure. I mean, perhaps it's worse now. Talking to the postdocs now, they do feel lots of pressure to publish. And you see also this in committee, right? I mean, when people say, oh, this person only has 3 papers, but this one has 5. So this kind of counting it comes from everybody. Yeah, there is pressure. I think it's as bad in math as it's in theoretical physics. In a way.
It's also my impression, yeah. Also, it feels to me that there's less, I'm not sure if this is accurate, but it feels to me that there's less kind of objective reality in theoretical physics. Like, in maths we have some conjectures, and no matter who proves it, it's going to be an annals paper, and this will look good on a job application.
Yes.
Whereas I feel like in theoretical physics it's much more fashion-driven, or...
There's a lot of fashion-driven work, yes. And so... very often grants are given on that basis, so you have people that work on this fashion or whatever. And that doesn't mean whatever is fashion, that doesn't mean it's not interesting, right?
Of course.
Things happen rather interesting. And of course, if you're a young or early career researcher, you want to get into that. I mean, it's natural in a way. But it's a bit too much,
And somehow... the first time that I heard both of your names was with the famous quintic paper.
Oh, okay.
And I think for many mathematicians, this is just an incredibly inspiring story. And I'd love to hear, firstly, could you explain for the layperson, like very roughly, what happens in that paper and why it's so amazing?
What happened? So there is a precursor to that paper, I think, right? This paper in which Philip and I wrote this paper, discussing the moduli space of Calabi manifolds. And we discussed the moduli space of the Kerr classes, of the moduli space of the complex structures. Now it looks like the trivial thing that everybody should learn, right? But at the time it wasn't so trivial. So we wrote this paper, but we have a chapter at the end. So at the time, mirror symmetry was being conjectured, right? We wrote this paper in 87 or something, 89, and the conjecture of mirror symmetry was a few years before that. And Philip had been working on this. Perhaps we can tell about this later. Had been working on this experimental evidence, of mirror symmetry. So then, for this paper, we said if mirror symmetry is true, the relation between these two modular spaces should be isomorphic. There should be an isomorphism map, which became the mirror map. But this is not a classical statement, right? So in the physics, what we knew at the time is that you had to include the quantum corrections to the theory, which this became on the one side the instant of corrections, which became mathematically the rational curves. So there is a dictionary, dictionary between the physics and the mathematics. So we knew that one side, the classical answer was correct. Didn't have any corrections, quantum corrections, sorry. But the Kähler class side had these quantum corrections associated to this instant also. So if mirror symmetry exists, I mean, one should be able to construct the map, right, and compute the correlation functions on each side of the theory. It's a physical theory, right? So compute correlation functions. So the 3-point correlation function became this Yukawa coupling, right, that we computed. So computed this classically on one side, and then that through the mirror map gives you the correct quantum corrected answer of the other. So this is what gives you this generating function of the rational, the counting of the rational curves, right? So it was a story that started with this paper, and then we implemented that idea for the quintic, right? So
and when was the quintic paper?
1990, 1991. Yeah. So for the previous paper was so the ideas for this second paper came from that. If you look at the last sections of that paper, the idea.
So there you said that such an isomorphism has to exist, but then for the quintic you could actually work it out and give these concrete predictions for.
Which involve computing all the geometry of the modular space, right, including these periods. It was quite a chunk of work.
And what are your recollections from that?
Well, it's pretty much as Xenia said. I mean, we've been working. So there was an idea that perhaps there was mirror symmetry because you take a space. So behind this is the physics idea that space-time is 10-dimensional. And to have a supersymmetric world, you want four of the dimensions to be Minkowski space and 6 of the dimensions to be a Calabi-Yau manifold. And then properties of the Calabi-Yau manifold tell you about the high-energy physics in our world. So it's high-energy physics in our world. It's really low-energy physics in the big picture. But it tells us about the physics in the 4-dimensional world. And in particular, the Hodge numbers, the topology of the Calabi-Yau manifold is reflected in the number of families and anti-families of particles. But it doesn't tell you which one is the one. I mean, you could have 3 families, as we believe there are, and no anti-families, or you could have 3 anti-families and no families. What you call a family and an anti-family is arbitrary. So you pick one, and then the other one is the anti-family. And so this meant that, for example, the Euler number you could change the Euler number of the Calabi-Yau manifold by a sign, and nothing would change in the physics. And so the thought was, well, perhaps Calabi-Yau manifolds, I mean, it's a weak argument, but it turned out to be true. I mean, perhaps Calabi-Yau manifolds always come in pairs. That for every manifold with certain Hodge numbers, there's another. So there's an H11, the number of 1 forms, and H21, the number of 2 forms, and for every one of these. This doesn't classify the Calabi-Yau manifold, but it goes quite some way to doing that. So for every pair of these numbers, there's another manifold with the opposite pair. And then that has consequences of the sort that Xenia said. And at the beginning, this looked very improbable, because if you looked at constructions of Calabi-Yau manifolds, then it depended a bit on who you were. So mathematicians tend to produce examples by the traditional means of algebraic geometry. So you write down a quintic, say, so you have a CP4 and a quintic equation, and that gives you a manifold of vanishing first Chern class. And you can generate lots of examples like that, very, sort of generalizations of that theme. And these always have Euler number negative, because the Euler number is the difference between the number of deformations of the complex structure. It's twice the difference between the number of deformations of the Kähler form and the number of deformations of the complex structure. And if you give an equation as with the quintic, you have a P4 with 1 Kähler form. So you have 1 parameter family of P4s, and many parameter family of quintics. There are many terms in the general quintic, and the coefficient of each term, roughly speaking, is a parameter. So you get hundreds of parameters of the complex structure, and perhaps just 1 parameter of the P4. So that's going to have a negative Euler number. In fact, the Euler number for the quintic is minus 200. And there are many examples like this where you give some polynomials in a product of projective spaces. So you have a few Kähler parameters corresponding to the projective spaces, and a lot of parameters corresponding to the polynomials. And so all those, so you produce lots of examples with negative Euler number. Now, meanwhile, some physicists had seized on examples that you get from orbifolds. So you start with a torus, a 3 torus, or 3 complex tori, and you make it less trivial by dividing by the group and resolving fixed points. And those always have positive.
A little bit like Kummer-Sepps.
A bit like Kummer-Sepps, generalizations of this construction. And those always have positive Euler number, because you start with a torus with Euler number 0, and then, as you say, you resolve lots of singularities, and that always increases the number of Kähler classes. So that gives you positive Euler number. So there were one bunch of people who said that it's clearly the case that there are more Calabi-Yau manifolds with positive Euler number than others. And then there were a bunch of algebraic geometers, basically, who said, no, it's clearly the case there are always many more Calabi-Yau manifolds with negative Euler number. So at the beginning, it didn't look as if there were equal numbers of these things at all, or then the classes of these things looked very different. And in fact, we had to sort of generalize the constructions, and you start looking at polynomials in weighted projective spaces. And a weighted projective space is sort of hybrid object, where you take a projective space, you divide by groups, and you blow up the fixed points, and so it's a mixture. You get a mixture of these two things, where you get the blow-ups and you have the polynomials. And then suddenly, when you started plotting, constructing lots of these, and just say, well, how many manifolds, examples like this can you construct? Then you construct thousands, and you plot the Hodge numbers on a graph, and then you see that the plot looks symmetric. So that was a wonderful thing. And
when did you first start seeing that kind of thing, like that plot that you just described? Was that already in the 90s or earlier?
That was in the 90s at about this sort of time.
Yeah, it was.
It was earlier. It was work I was doing with some graduate students. Yeah, and then at that same time, I was also Xenia and I were working on the moduli spaces, because if these two spaces of Calabi-Yau manifolds are the same, then their moduli spaces, the parameter spaces of the manifolds, have to be the same. And again, that didn't quite fit, because there's a natural geometry on the complex structures, and there's a natural geometry on the Kähler classes, and it's different. But we know that the Kähler classes get corrected through the quantum corrections. So if you now say, well, if it really is the same, then you know what the correction has to be. And then from another way of looking at it, of course, ultimately you're analysing path integrals, and one way of looking at a path integral is to study it by steepest descents. And then you look at, you have a series that counts the number of stationary points in the integral. And it turns out that for supersymmetric cases, this sum, which you would normally think is just an approximation, is in fact exact. It gives you a series which converges, and then the terms in this series have very beautiful interpretation as sums over the rational curves in the mirror manifold, and or the corrections in the sum of the rational curves in the original manifold.
So just briefly, so I think that we've probably lost the lay audience at this stage, but maybe one can say that you made some predictions for things that mathematicians really cared about, some counts of rational curves or something, which then, I think initially the predictions were basically met with disbelief. Is that?
Well, 1 and 2 were known, right? So the numbers of rational curves in the quintic, so you can embed a P1 holomorphically into the quintic as a by linear equations, or by quadratic equations, or by cubic equations. So there's a degree associated with that. So the number of instantons of degree 1 was known. It was calculated by Schubert. It goes back to Schubert. And Schubert, in fact, he calculated it twice. So he was a mathematician, and he proved it once. And just in case, he calculated it later again in his career by different methods and proved it again, and got the same.
And it became a Hilbert problem to put these computations on a rigorous footing. So
I see.
So Schubert had all these methods, and they were very intuitive. And I think that there was some degree of disbelief in, like, he's very effective, like just extraordinary at doing these computations. But then one of the Hilbert problems was to rigorously,
Right. And then, but the way we did the calculations was they're just manipulations on the periods. And you can, especially if you have a computer, you can just carry on. And there was a third number. And then there's a third number. And the third number is 317,206,375. Right, so...
Can you say it again?
So, it's 306,375 is the number of cubics. Okay. And we were just at the stage where Ellings, Rudenstrom
That's true.
were looking at this.
Uh-huh.
Again, because even the mathematicians needed a computer to do this.
Yeah.
And they needed several computers because they did parts of the code, parts of the calculation with one algebra package and parts of the calculation with another algebra package. And so they did a computer calculation which was quite complicated, involving transferring results from one program to another, and so on. Anyway, they came out with something else. It was off by a lot.
Ah, okay.
It was off by a lot. This was the first year, so for a year, it took a year to sort
But it was
out.
more striking because we were not just predicting that number, we were doing a generating function for the numbers, right? So it was really much more.
So, and then the community sort of divided. So the algebraic geometers say, well, you know, these are good guys and we understand their method in principle, even though the calculation is complicated, and they must be right and we've got to support them. And the physicists were lining up and saying, look, you know, if you read this paper, you see how it's done, and this is the answer. And it took a year to resolve. And it turned out to be some elementary thing that was wrong in one of these computer codes.
So an engineering issue.
It was some. You initialize something and you say do from n is naught to something, okay. And they should have said do from n is 1 to something,
okay.
Something like that.
Uh-huh.
And once you correct that, then you get the answer. So there was a.
And can you remember when you first found out that the algebraic geometers agreed?
Yes, there was
an email from Clemens.
Yes.
There was an email from Clemens one day, and Xenia was down in Costa Rica teaching at the university. Yes, she had returned, as she said. And I get an email from Clemens that simply said, "Physics wins."
Yeah.
Was that it? Dear Philip.
Yes, dear Philip.
Physics wins.
Physics wins. It was strange. I mean, it was a different world then. For example, you would talk to a mathematician, and some mathematicians wouldn't even talk to you. And if they did talk to you, they'd say, "Come to my office," and they'd close the door. Because they didn't want it to be seen that they were talking to a physicist.
Really?
And some people thought it might impact their tenure prospects or...
Really?
Yes, it was a disreputable thing to do.
It wasn't talking, it was collaborating, right? It was
like conversations could turn into collaborations.
Writing collaborations.
That's extraordinary. I was totally unaware of that.
It wasn't that way. I mean, only some people, I think. It wasn't.
And then I guess so it must have shifted massively in the 90s, because when I grew up mathematically, to talk to a physicist was a very positive thing.
Yeah.
It certainly helped.
Yes, but it changed. The world, certainly attitudes changed. I mean, prior to that, mathematicians had always gone first. This was an instance where, in fact, that because we have this model of the world in physics, that we could see things that at the time were not appreciated in algebraic geometry.
But surely that was also the case with path integrals and QCD
but path integrals weren't respectable.
Okay, so this was the first time that it was respectable for a mathematician.
It wasn't possibly the first time, so Atiyah and Singer and others had done important work, as you say, in gauge theories, understanding things that physicists were telling them, and so on. But there was a lot of feeling that this involved path integrals, and the path integral was a black arc that was infinite and couldn't be defined in mathematics, and so on, and that physicists were talking about things that they didn't understand, which is in part true, and so on. So the world has changed. Xenia and I have been working in number theory for a number of years, things to do with number theory. And again, you want to talk to a number theorist. It's not really respectable to talk to a physicist.
I wouldn't put it like that. I think very often what you do is not considered rigorous, right? So it's not, which sometimes it's not.
No, it's not.
But sometimes it is, actually. Sometimes it's rather...
Yeah.
I guess I would, so I think there's two things going on. One is that lots of mathematics is very conservative, and I think that that's also somehow nice. It also means that mathematicians are kind of anti-hype, and and that's a very nice aspect. But also I think that there's a degree of intimidation. Like certainly when I speak to some physicists, I just have no idea what they're talking about. And so it's really difficult for me to even start a conversation. And
that is a language. At least in part, it's a language issue. And how do you infer from what you know when you claim that something is true? I mean, if you don't, when was Witten's Fields Medal?
It was about
in the 90s, yes. So, okay, the 90s.
Because I think this is widely seen by some as a kind of testament to the increased dialogue between. And how do you see if you imagine a graph throughout the centuries of mathematics and physics interaction, how would you characterize it over the last 3 decades?
Really rich. I think the interaction is fantastic. I mean, what happens is that our field is so mathematical that we tend to interact quite a lot with mathematicians.
Yes.
Despite the fact that, as you say, something we don't understand each other. I mean.
There's definitely much more.
But that's our own. We are biased by our own research area. But string theory, I mean, the interaction that has come from that in mathematics is huge.
What? If I can ask you both, what are you proudest of your achievements?
Depends on different stages in my life.
Do you have to choose one?
I have to choose one.
Yeah.
Oh, I don't know. The moduli paper I was talking about. Because that one had the ideas in some sense. Of course, the quintic brought this to life, right?
Yeah.
In some ways, it was just an idea. So that's very proud of. But I am also very proud of the number theory, the things that are happening now.
I'm interested in what role homological mirror symmetry plays for you, because for us mathematicians we love it, but
yes, we never talk it for some reason. We don't. I always wondered whether we should have some sort of small learning group with mathematicians and get to know more about homological mirror symmetry. Whether we have something to say about it. It's, I suspect not. I think it's quite, maybe, who knows? I mean, it's, we never talk about homological symmetry.
And maybe if I just made one more technical question. So I remember when I learned about Bartyrev's reflexive polytopes. That you use also. Okay.
Yeah.
So I remember that Bartyrev, we were at the time in Switzerland.
Yes.
Bartyrev came and gave a seminar at CERN to the theory group. And Bartyrev, great guy, I mean, but he's a hardcore algebraic geometer. And he was talking about these homotopes. And I think it's fair to say that no one in the audience understood what was going on. And then, of course, thinking about it and working and then seeing that this was in fact incredibly useful, sort of changed the entire direction of our work for years. And Sheldon was sort of explaining this
To us,
to us in terms that we could understand.
So we were trying to connect with the physical.
An important role was played by people like Sheldon Katz and Dave Morrison, who could sort of translate.
Yeah, they're so important, these people that can, the translators.
They can translate from one language to the other.
So that has changed. There are more people like that now, right? We get students in Oxford. I mean, one of my students came with 2 degrees in mathematics. And he can talk, and he's one example, right, of many.
Well, I guess the quintic paper, or the work around that, so the establishment of mirror symmetry, and then further work afterwards, there were more. The quintic was easy, but it wasn't easy, but it's much easier than some things that came afterwards. The more complicated examples were important because they forced a better understanding, a better notation, forced you to sort of clarify issues. The work on the mirror manifolds was much more intricate. And of course there was this drama when people said that, no, actually, what you say is very interesting, but it doesn't work, right? To do with the cubics.
Yeah, I mean, it just makes such a great story, and it's also, I've had that experience to a much lesser extent where you think that something's correct and someone else thinks the opposite. It really is a very interesting kind of psychological journey.
No, it really makes you think, well, I have an argument, but do I really believe every step?
But I'd love to just ask you what you think about the current kind of disaffection with string theory, I would say.
So you have a theory that on the one has produced an enormous amount of results, right? In mathematics, and there's also this whole bunch of ADS-CFT correspondence that has found its way to condense matter. Right? So it has produced, it has been very fruitful, producing ideas that could be applied also somewhere else. So, on the other hand, many of the criticisms come from people who say, well, predict something correctly from the physics. Well, fair enough. You're a physicist, you want a theory that predicts what you see, right? But at the moment, the theory is such that you cannot do that. So you either throw it away as a physical theory and continue using it as a ground for a new idea, or continue with it and see whether you eventually can say something about the world. Right? But I think research kind of goes the way it goes. I mean, it's also criticism into the amount of money that is going to that. This is theoretical.
But it is a very important question where money goes, and
it is.
We can certainly, you can spend a lot of money pursuing something that doesn't turn out. Or
maybe the string theory is not their theory. That might be the case. I mean, but still, you cannot take away the enormous amount of new ideas that have been produced into that.
People say that string theory is very, very valuable for mathematics, but it doesn't tell us much about physics. And that's an exaggeration, that's a caricature. But I don't think that can be true. String theory clearly is consistent at many levels. It's clearly a very deep theory, and it's consistent at many levels because where it affects mathematics, it's been shown to be correct. I don't think that you can have a theory that's as rich as this and consistent, so true in some sense, and not have it apply, and it applies to the physical world in some way, and it solves problems that were previously insoluble, like putting together general relativity and quantum theory, which was something that resisted solution for many years.
One can make a kind of devil's advocate argument that any mathematical theory which is true has some impact on physics.
I mean, eventually we will crack this. It's slower than many expected, and that's true. And people are anxious, what will we see next at CERN? Well, I would like to know that as much as anybody.
Mm-hmm.
It's also true that experiment has been very important in developing these theories.
Mm-hmm.
That there are many things that we wouldn't have thought of in isolation.
Yeah, it's somehow a really beautiful dance, the experiment theory dance. And
yes.
And I also think that like many people criticize string theory because it's so, in some sense ahead of experiment, but that's also been the case historically with general relativity. And
yeah, you have a theory and it may tell you about things that you can't measure yet, but nevertheless, you have a theory, you best explore the consequences of the theory. You can think about it even if you can't, even if it's not practical to measure all the consequences.
Thank you very much. This has been very, very interesting for me.